as was announced, I'm going to talk about the title is Mensuration of Quadrilaterals in Lilavati. At the outset, let me mention that my study of Lilavati is not particularly detailed, and whatever I studied is not from the point of view of the language or alankaras or anything. It's more about the mathematics. Now, just as the translations do not capture the literary aspects, there are also certain mathematical aspects that do not get captured in the translations. The translations usually tend to be from sutra to sutra to sutra and so on, and then sometimes you don't quite see the pattern of whether if there is a strand of mathematical thinking that is not always come through. I mean, the Kolbuk's book has various comments, but there's a lot more that may be hidden in the text from a mathematical point of view than meets the eye, than just what one would get from reading the translations. Now, here I'm going to focus on the aspect of areas of quadrilaterals. Has been a kind of tricky topic in Indian mathematics. Now, the history of the area of quadrilaterals goes back at least to Brahmagupta, if one is to think of more general thing. Of course, for the symmetrical trapezia, etc., there are the areas were already used in the Shulva Sutras. So, with regard to the mensuration of quadrilateral, one can go back to Brahma Sputa Siddhanta, and the sutra Sthula Phalam Trichaturbhuja Bahu Pratibahu Yogadala Ghatat Bhuja Yogardha Chatushtya Bhujona Ghatat Padam Sukshmam. Now, I'm sure many of you can translate it for yourself, but here is the, traditionally, the sutra has been translated, there are two parts. Okay, the gross area of the triangle, of a triangle or quadrilateral is the product of half the sum of opposite sides. So you take the average of the opposite sides at the size and take the product of the cross. For the cross, and that is given as the approximate area. The exact area is the square root of the product of 4 sets of half the sum of the sides diminished by the sides. So you take the sum of 4 sides, halve it, subtract each of the sides separately, take the product, and take its square root. That is that is given to be the exact area. Now, so it turns out first of all, as many of you know, the formula is really not exact for a general quadrilateral, and it is exact for cyclic quadrilaterals. That is when the quadrilateral is the vertices of the quadrilateral are lie on a circle, then the formula is exact.
Second line.
Chatushtaya, yeah. Yeah, sorry. Yeah, there's an A missing here. So, yeah, sorry, yeah. There's an A missing, the Chatushtaya. Yeah. Going back to what I was saying, exact only for the cyclic quadrilateral, according as we know it. Now, the general perception so far has been that Brahmagupta somehow omitted to mention the condition, though he was aware of it. And of course, he has applied it only in the case of cyclic quadrilateral. There is no mistake in application. It has, however, recently been argued by Krishnaswamy that, in fact, this interpretation of the sutra itself, the translation itself, is not quite correct, and especially with regard to the term Trichaturbhuja. What does Trichaturbhuja mean? That, as we saw, it was translated as triangle or quadrilateral, that it applies to both triangles and quadrilaterals. However, Krishnaswamy argues quite convincingly, I think, as far as I'm concerned, that Trichaturbhuja was designed by Brahmagupta to mean a cyclic quadrilateral. It did not mean circles or quadrilaterals, but a technical term, so to speak, for a cyclic quadrilateral. So Brahmagupta actually did mean that the gross area of a cyclic quadrilateral is the product of half the sum of opposite sides and the square root of the product of etc. etc. So this to be the exact formula for cyclic quadrilaterals. Now the reason for this terminology, this term can be a sort of, I don't know if I have said it here. The origin of this term sort of comes through, if one, according to Krishnaswamy, in the following way. So Brahmagupta had been studying the triangles and their circumcenter and circumradii, and in the process, I mean, he went to quadrilaterals which arose from the triangles by adding a point on the circumcircle, and then those quadrilaterals were automatically cyclic quadrilaterals, and the formula applied to them. And Krishnaswamy has a paper in Ganita Bharati where he gives a detailed argument about how Brahmagupta would have proceeded to derive this formula, which is what makes it more convincing, I think. However, I think the knowledge of Brahmasputa Siddhanta did not go directly, though of course there is when talks of continuity in Indian mathematics, it did not go quite directly in that from Brahmagupta to the later people. And in a lot of this subsequent literature, the condition of cyclicity has been completely omitted. So I have listed here a few people. So Sridhara, there's a comment here. Sridhara, I think in one of the earlier talks also was mentioned to be from 11th century. But I may mention that recently some of these people working with Jain mathematics especially, they have identified this Sridhara to be from the 8th century. There is a thesis by Shefali Jain, which is my reference for this. Anyway, that's a side issue. So in Trishatika, he gives treats this to be a formula for any quadrilateral, and in particular applies it to even a general trapezium. Same thing kind of holds with Mahavira's Ganita Sara Sangraha and Siddhanta Shekhara of Shripati, also have this formula treated as if it is for a general quadrilateral. Mahavira does not quite give examples with quadrilaterals. In fact, it doesn't give examples with quadrilaterals. The examples are restricted to triangles, so in which case the formula is true anyway. But in any case, the condition, the formula is stated unconditionally, so there is no cyclicity implied. And I think that the practice of such a thing was so prevalent that even in the 14th century work of Thakur Feru, the Ganita Sara Kaumudi, which was edited by for guests here, Dr. Sharma and others, there also the formula is given unconditionally. So I have just made a general comment that notwithstanding all the overall continuity in Indian mathematical tradition, topics these special difference here is that it was probably not a topic which was pursued, applied or pursued regularly. So the knowledge about that sort of did not go, they suffered, the practice of that suffered neglect. So we now come to Bhaskaracharya. Bhaskaracharya states it's stated Sarvador Yutidalam Chatushthitam Bahubhir Virahitam Cha Tadvadat Moolam Asputa Phalam Chaturbhuje Spashtameva Muditam Tribahuke. So it is here it's no longer meant to be exact formula for the area of a quadrilateral. He qualifies it by saying that Asputa Phalam, Moolam asfuta phalam. So how to interpret the word asfuta, one can debate a little, but I'm not going to deal with that. Anyway, so it's a certain qualified statement. So typically it has been translated as inexact. Maybe one could be content with that. And then emphasizes that in the case of triangles, it is meant to be exact. It's pronounced to be exact. Spashtameva uditam tribahuke. Okay, so now here are some comments. And now Bhaskara was not the first one to recognize that there is something wrong with with that as the area of any general quadrilateral. Aryabhata, the second before him, also noticed that there was something wrong, so but he outright rejected it as having anything to do with quadrilateral and accepted it, the formula only for triangles, the analogous formula, which is called the formula of Heron of Alexandria. So now, unlike Aryabhata, Bhaskara actually does involve himself with the formula, but calls it, to begin with, he calls it inexact, asfutam. But that is actually only the beginning. I mean, if one follows through the sequence of sutras that follow, there's a variety of response that one can see on Bhaskara's part, which I think is very interesting, and my talk is mostly about that. Now, right after saying that it is inexact, there is an example where in the next sutra, this is 168 according to Colebrook's numbering, he gives certain values and asks to compute the area as told by the ancients. And the description of the quadrilateral is the base is 14, face is something wrong here, but anyway, the 14th, 14 face. Okay, so there's an asymmetric trapezium of which the figures are given, and then he first asks you to ask the person who is addressing to compute as told by the ancients, and then in the commentary, annotated commentary, he proceeds to note that the area as given by the formula would be square root of 19,800, and this which is notes that is a little less than kinchit is the adjective here, less than 141, while the actual area which can be computed because it's a easily because it's a trapezium is 138, thus pointing to a contradiction in a certain way, or perhaps that it is approximately true. Exactly what was meant would be difficult to say, but he shows that there is a difference. The formula is not exact. Now he then embarks on more detailed discussion on the issue. And at the beginning of Sutra 169 in the Vasana Bhashya, there is it says Atha Stula Nirupanartham Sutram Sardha Vrittam. I can't say it from here. Sardha Vrittam. So now, of course, as we know, Atha marks for the commencement of things. So it's starting of a story or a chapter or argument, etc. And Nirupana means analysis. So and here, notice that here he uses the word sthulatva, and it's not the noun form of asfutam. But here there is a different adjective used here. There is a sthulatva to the formula which is going to be analyzed. So Bhaskara announces here that he is taking up an analysis of the grossness of the formula. now, somewhat curiously, in Kohlberg's translation, this line is not translated. It's there in where the full text is given, but this line is not translated. So one might miss the fact that there is a new, fresh analysis being taken up by Bhaskara. Okay, that sentence is followed by the sutra which says the diagonals of a quadrilateral are indeterminate, aniyatau. Then how could the area be determinate? So, in other words, the values of sides do not determine the quadrilateral, then how can you ask for it? How can the area be determinate? So here he assumes somehow that maybe for good reason, the values for diagonals set down, that is prasaritau, by ancients would not be the same elsewhere. So if they computed it for certain values of diagonal, he assumes that some additional information is needed, and like diagonals, and obviously they must have assumed some values, but they would not apply in all cases. The same choices of the sides, the diagonal have many possibilities, and the area would vary accordingly. So therefore you cannot have a formula. Now this is further elaborated, noting and this is the main part of Lilavati, and the annotations. Bhaskara adds the following. You see that if in a quadrilateral two opposite vertices are moved towards each other, then the diagonal between them contracts. That diagonal will become shorter, and the other diagonal elongates. Thus, with the sides of the same length, there are other possible values for the diagonals. So the area is not automatically fixed. So then this is followed by a rather rhetorical question. When none of perpendiculars are either none of the perpendiculars nor either of the diagonals are specified, how will the other values get determined? Thus it amounts to asking for definite area when it is actually indeterminate. So that's a point. And this is followed by a rather devastating blow, which says such a questioner is a blundering devil, Pishacha, and worse is the one who answers it. So there is a damnation of the people who don't seem to recognize. So there is, one sees the image of a scholar who has noticed something is wrong, and then trying to pursue with all the strength, with all the might at his disposal to demolish the false impression. Okay, so they do not realize, worse is the one who answers it. They do not realize the indeterminate nature of the area of a quadrilateral. Okay, so then that's not all. I mean, it does not stop there. See, having vented his ire on the ignoramuses, the Acharya next sets out to establish the point through more concrete illustrations. Okay, so and now before going forward, let's point out that the argument that was given in terms of moving the vertices closer, though it has considerable heuristic value, it's not conclusive. Because so far you didn't show that there could be various different quadrilaterals, but the area could happen to be the same. So far we are not actually seen, despite its heuristic value importance, one has not so far seen actual examples. And to confirm that the reasoning is valid, one would need specific examples with the same sides. Same size for 4 sides and different diagonals for which the areas are actually different. That's what one would like. So whether specifically with this realization or not, that is what Bhaskara sets out to do in the sutras that follow.
There is also the formula for the diagonals. He may be just arguing that the diagonals are not fixed by the sides.
No, that comes later. His sutras on diagonals come later. They are not in this part.
No, but it is in his mind when he...
Yeah, right. No, in his mind, certainly the data for a quadrilateral should consist of sides together with a diagonal or a perpendicular. Okay. Now, and now how does he plan to do that? He goes as follows. So for the illustrations, one needs examples where, as I said, we need to actually be able to produce, to be able to get the things closer and still be able to compute the area. It's important. For this purpose, he considers rhombuses, so the quadrilaterals with all sides equal. And he notes, so for rhombuses, he notes the formula for the interrelation between the diagonals. So if you have one diagonal is d1 square and the side is a, then the second diagonal is described to you. When this is simply an application of the Pythagoras theorem, you will get that d2 is square root of 4a square minus d1 square. This will be the relation between the two diagonals. And then he also recalls that the formula for the area of the rhombus will be half of the product of the two diagonals. This is in Sutras 774, 75. While talking about the area of this rhombuses, he also adds about the area of trapezia and the rectangles, and the translators dutifully include that also, and then you sort of are puzzled about why is this formula for other things coming here. But the thing is that is merely the kind of thing that a teacher would do, like when you are recalling the area of a rhombus, you might in a general way say that for trapezia it would be this, etc. So it's a digression which when reading the translations can be distracting. Okay, so that's a comment. So here he's mainly concerned with in applying this to his argument to these rhombuses, and this is the formula for the diagonals, and that's the formula for the area. Now, so at this juncture, where one is in a position to argue that if we start with a rhombus with a side A and diagonal D1 and move the vertices closer, then the area will be given by this thing with A is fixed and D1 is variable. Now in this expression, it's easy to see that when D1 varies, even if A is constant, with D1 this value is going to vary. Now he's not content with this formula, general formula, would like to actually construct specific examples, and for that he bases himself on Pythagorean triples. So if you have a Pythagorean triple LMN, then that gives you the right angled triangle, and by putting together 4 such right angles in a symmetrical way, you get a rhombus with sides whose gets a rhombus with all sides n, and the diagonal, the sides will be the diagonal now. Diagonal of the original triple will be the side, and the diagonals of the rhombus will be 2L and 2M, so the area will be twice LM. Now comes the interesting part. He chooses 2 such triples, 5, 20 and 25, and 7, 24, 25. So the 2 Pythagorean triples with the same value for the diagonal, but different values for the sides. Okay, and therefore now when you construct the rhombuses with these 2 triples, they will be different shapes. For these 2 rhombuses, the area can be computed. One this will be 600 and this will be 336, which is substantially different. So we knew that they're quite, they can be quite different. And to this, he also adds the example of a square with side 25, which can be compared with this, in which case this area will be 625. So there is an elaborate picture drawn to say that the earlier belief is wrong. Now, So Bhaskara adopts various means, argumentation, pressurizing through rhetoric and persuasion, to put across the readers that Brahmagupta formula is not valid exactly for a general quadrilateral. It's the first time I think that the clarity on the formula to an extent is generated. For the group of sutras that follow, there are two more problems concerning the area of a quadrilateral, and I'm going to focus on the second one. The first one is again another trapezium in which is not symmetric, and therefore the formula does not hold. So there is one more confirmation. But the one that I want to sort of discuss with little detail is the following. In Sutra 178, he has to find the area and diagonals and perpendiculars for a quadrilateral whose sides are given as face 71, base 75, left side 68, and right side 40. So these are the sizes given. Now, this comes right after the discussion that we had about the areas of quadrilateral, and one would puzzle why how come such a problem is asked. Here, notice here that area and perpendicular are asked just on the basis of sides. So, as I said, to a modern reader, it should seem puzzling that Acharya should ask such a question giving only the sides, after the painstaking endeavor to get it across that sizes of four sides do not determine a quadrilateral. Now, the interpretation I could think of is the spirit of this. What I'm going to say is in no way final. This is an interpretation that I could think of. Is the spirit is that to be able to explain how one should proceed in response, such a problem is posed. So, since in the earlier times, the focus was on cyclic quadrilaterals, and these were determined by four sides. So there was some idea of concept of thinking of quadrilaterals in terms of four sides, and what is being dealt with here is how one would respond to a question posed in this fashion. So in the following sutra, again, he emphasizes that if we know the diagonal, then we will know the perpendicular and vice versa. And so one datum is again needed, and then he proceeds to determine, and this part is not there in the main part, but in the annotation it's there. To determine the perpendicular, we assume the diagonal joining the tip of the left side to the base of the right side to be 77. This value is rather curious. So one should note that if one took an arbitrary integer, you would not even be able to compute things very neatly, and it won't be any illustrative example of any sort. So he then proceeds to compute the area using 77 as the value of the diagonal, and that turns out to be 3234. That is the value. Is actually this value, I must say, is here he computes it by first computing the perpendicular, then the area of the two triangles, and adding it up. Rather surprisingly, he doesn't use the formula for triangles. He doesn't use Brahmagupta formula for triangles. Though there is another place where the computation is made for triangles, and then he confirms that it is true. Okay, so now the interesting thing is that this is the value that would get with the formula star. That value that we saw is exactly the value you would get for the given values, and the reason is not surprising, because that is the value when diagonal is 77 is when the quadrilateral becomes cyclic. So the formula is applicable, and therefore it coincides. So reason for this, Now, I have commented here, it's curious that the choice was made in such a way that the quadrilateral is cyclic, while there is no reference to such a concept in the text. Okay, so, and the explanation for this is that though the values in some way were familiar to Bhaskaracharya in another way. So, and this is the following. How was that? Yeah, here I have said that, raised the question about why this was chosen, and the commentators have thrown no light on the arbitrariness, not even commented on the arbitrariness of choosing 77. Okay, so it seems that the quadrilateral was familiar to Bhaskara. Brahmagupta had given a construction in Brahmasputa Siddhanta for constructing cyclic quadrilaterals, starting with a pair of Pythagorean triples. Now, Brahmagupta's construction itself will produce, first of all, the Brahmagupta direct construction gives cyclic quadrilaterals in which the diagonals are perpendicular. So that still leaves one puzzling why, but on the other hand, in the case of Bhaskara quadrilateral, the diagonals are not perpendicular to each other. But from the Brahmagupta construction of cyclic quadrilaterals, there is a way of modifying that. What you do is that you have the cyclic quadrilateral, draw one diagonal, and one side of the triangle you reflect in the in the perpendicular to the chord to the diagonal. So you get another cyclic quadrilateral with different sizes, and Ganesha has observed that this quadrilateral 51, 67, etc. does arise from such a construction, which was and the Brahmagupta construction as well as this modified construction do feature in the Lilavati. Though this particular example is not worked out in Lilavati, there are similar other things that are constructed. So it seems clear that he was aware of this these specific values and chose accordingly. Thank you.
The fact that that formula is an exact formula of a triangle and inexact for quadrilateral. At that point, Ganesha tries to give some argument for a general quadrilateral. But that argument is not understandable for the reason we were discussing. It says darshanam in two places. The diagram is not there.
Yeah, Colebrook also comments that it's not Colebrook, perhaps the Banerjee who produced the edited version has commented that it's
I had another question. It would be inconceivable to think of Brahmagupta not knowing the area of a trapezium.
Pardon?
It would be inconceivable to think of Brahmagupta not knowing the area of a trapezium. And that's one case where we would have tried to try out this formula.
No, the thing is, he was primarily working with triangles and circumradii, etc. In the context of which he
chapter on the 13th chapter.
Yeah. Yeah.
Yes, much more complicated areas.
So, but for him there is no contradiction. This formula is for cyclic quadrilaterals.
No, that's what I'm saying.
Yeah.
Brahmagupta would have known that.
No, that I think is unquestionable. Brahmagupta definitely.
That's what I wanted. I mean,
yeah.
Understanding whether Sinaswami's interpretation is right or not.
Yeah.
That means that Brahmagupta knew that his formula was.
I don't think there is any doubt at all that Brahmagupta knew what he was doing. There is no issue about it. It's only that in the subsequent period, I think the
knowledge has been
lost. Yeah.
So we are already running out of time. So if there are no other questions, we thank all the three speakers for this.